Okay, today what we're going to talk about is the application of exponential functions to interest in finance. Now, it's pretty straightforward. When you put your money in a bank account, you would expect that money to grow by a certain percentage. This we would call as our basic standard function. I'm going to let A equal the amount that you have at any time, T. And T is going to be in years. So my base formula is going to look like this, where A naught is our initial amount, B is our factor, and T is our time. We use this formula when we have what's called an annual interest rate, or sometimes referred to as compounded yearly. An example of this would be a simple bank account. Let's say you go and you deposit $1,000 in a bank account that pays 2.5% interest annually. So, your savings account at any time in the future, as long as you don't take any money out of it, could be described using this formula. My 2.5 is, of course, your big R. Little r is going to be 0.025. This is the amount that my factor is bigger than 1. Raised to the t.
Mr. Hall, you know if you add or subtract them?
Once we have a formula, we can use this formula to find out how much money is going to be in the account at different times in the future. For instance, I could ask you how much will be in the bank account in 10 years. So, how much will be in the account in 10 years? In this case, all I have to do is understand that my T equals 10. So I can directly plug in and plug that in my calculator. Of course, I'm going to have to round a little bit in my calculator. Let's see, what do I have? 1,000 times 1.025 raised to the 10. I should have about 1,280.08 in my account. So in 10 years, I'll have $1,280.08. By the way, bank accounts always round down. Credit cards, loans, always round up. Okay, we're going to do another problem. Let's say you deposit $2,000 in an account paying 3% interest. Question, how long until your money doubles? Okay, first thing we're going to do is set up a formula that will describe how much is in the account at any given time. So I'll start with letting A being the amount in T years. With this formula, both this input and output, my formula is going to look like this. Let's see, 3% means my big R is 3%. Little r is 0.03, which means my factor is going to be 1.03. So now I have my basic model of how much money is going to be in my account at any given time in the future. So, first part, set up the formula. Second part, we're going to address the question, how long until your money doubles? Well, with the mathematical formula, you can do one of two things. You can either solve for t or you can solve for a. You can either look for the time or look for the amount. But to look for one, you have to know the other. In this case, we're looking for how long, which means I'm looking for a time. That means I must be able to determine the amount. Well, how much will I have when it doubles? I put in 2,000, it's going to double, the amount will be $4,000. So that means when it doubles, what's doubling? How much I deposited. So I'm going to have $4,000 in my account sometime in the future. I'm going to solve this equation. I'm going to solve for t by taking both sides and dividing by 2,000. I'm now going to solve for t directly by using the definition of a logarithm. And watch how I read what I write. T is the exponent I place on 1.03 to get the value 2. If I'd like to use my calculator to approximate this number very accurately, I'll do a base change, maybe the base, let's do base E. ln of 2 over ln of 1.03. Now we can just plug that in the calculator, just like it looks. Let's see, ln of 2 divided by ln of 1.03 is 23.49 approximately. Not 49, 44, 45. Rounded wrong. Years. So, I set up the formula. I realized I either knew the input variable or I knew the output variable amount. I plugged it in and I solved using whatever technique was necessary depending on what I was looking for. The next type of finance formula we're going to look at is called compound interest. Now, this is a more complicated formula. A naught is the initial amount deposited or borrowed if it's a loan with an interest rate of R compounded n times per year. Okay, we're going to set up a formula to describe the situation where you borrow 12%, borrow $2,000 at 12% compounded monthly. Now, three things I need to figure out from the word problem. What is the initial amount? Whether it's a deposit or a loan, in this case it's a loan. Initial amount is $2,000. So, that's my A naught. I need to determine my rate. Well, this is big R here. If you know big R, clearly you know little r. And last but not least, you need to determine n, and n is the amount it is compounded per year. In this case, if it's compounded monthly, we know that n equals 12 because there are 12 months in a year. So when I set up my formula, my initial amount of $2,000, 1 plus 0.12 over 12 to the 12t. Now, here's what's very interesting about this formula. What I'd like to go back to for just 1 second is that every single exponential function has 4 components. Every single exponential function can be written in the form, in this case, our generic exponential function y equals a times b to the x. This is generic for everything, where x is your input, y is your output, a is your initial value, and b is your factor. I'm going to change the form of this formula to that original exponential form. To be able to do this, I must be able to identify the factor. What I'd like you to notice, t is my input variable. T is not the factor. A is my output variable. That is also not the factor. The 2,000 in front is my initial value. The initial value is not the factor. I have 4 components of an exponential function: input, t, output, a, initial value, 2,000, and the factor. I've identified 3 of those 4 components. That means everything else must be the factor. The factor of this exponential function is 1 plus 0.12 over 12 raised to the 12th. Throw that in your calculator and let's get a decimal approximation.
1.01.
Let's see, parentheses 1 plus parentheses 1 plus 0.12 divided by 12, close parentheses, raise it to the 12th, gives me 1.1268 approximately. Why would I want to do this? This is a very important thing to understand, especially if you're ever taking a loan out. You were told that the loan was 12%. However, I just showed you that I could rewrite that same formula this way. The blue formula and the red formula are the same, except for a small rounding error in my calculator. That means 12% compounded monthly will cause my debt to grow by 12.68% a year. Let me repeat that. 12% compounded monthly means my debt does not grow at 12% a year. It grows by 12.68%. Look at your rate inside of this blue formula. This is very interesting. Have you ever wondered why, if you receive a credit card offer in the bank, from a bank, you'll have 2 interest rates? Always two. One small that they advertise and one always a little bit bigger. The little bit bigger one would be the 12.68%. The one they advertise is 12%. Let's take a look at the same formula. Instead of talking about compounding it monthly, let's say you borrow that same $2,000. They tell you they're going to charge you the same 12%, but this time they tell you they're going to compound your interest daily. So same loan, $2,000. Same stated interest rate of 12%. But just this a little changing of words to compounded daily. Let's see what happens. When we compound something daily, n equals 365. So are we still paying the same 12%? And the answer to that is no, you're not paying the same 12% because compounded monthly is very different than compounded daily. Let's take a look at that. Same loan, $2,000. Same little r, 12%, but n is 365. So if it's a different interest amount that they're actually charging you when they compound it daily, how different is it? What are they effectively really charging you? How do you figure out that? It's very, very simple. We need to find the factor. How do I find the factor in an exponential function? I eliminate everything that's not the factor. The input variable t is not the factor. The output variable a is not the factor. The initial value 2,000 is not the factor. So what is the factor? The factor is 1 plus 0.12 over 365 raised to the 365, and if you plug that in your calculator, divided by 365, close, raised to the 365, I come out with 1.127, I'll call it 5. Let me go up here. I started off with 12% compounded monthly, and I told you, in effect, they're charging you 12.68% interest. I still have 12%, but now compounded daily, and in effect, they're charging you 12.75%. That doesn't seem like it's 12% anymore. Makes you ask the question, just how big can this 12% get? How do I make it bigger? More time. Instead of multiplying it by daily, or compounding it daily, I could compound it every hour, every minute, every second, every nanosecond. There's an interesting naturalist named Euler who came up with a number called E. He was working with flowers, however, his number E is defined by this situation here. What he discovered was that if more and more times that you compound this, so as I compound this more and more and more and more, that is the factor of the compound interest formula. That's just the factor. What Euler discovered is as n gets bigger and bigger and bigger, in other words, daily is 365, hourly would be 365 times 24, which is huge. Every minute, the n gets bigger and bigger and bigger the more times I compound it. What Euler discovered was this was approaching Euler's number raised to the r. And that's where the number E comes from, which is approximately 2.718. Giving us our third and final finance formula called compounded continuously. So notice, all I did was replace the compounded factor with e to the r. Then I have my compounded continuous interest formula. Let's go back to the same problem we had before. You're going to borrow $2,000. They're going to advertise to you that they're charging you 12%. But instead of advertising it as being compounded monthly, or instead of advertising that it's going to be compounded daily, they're going to tell you that they're charging you a 12% continuously compounded interest rate. So, 12% compounded continuously looks like that. Same loan, $2,000. Same stated interest rate, 12%. So what's different? Let's find out by examining the factor. To examine the factor in an exponential function, I must eliminate everything that the factor is not. T is my input variable. It is not the factor. A is my output variable. It is not the factor. The 2,000 is my initial amount, in this case my loan, which is not the factor. So my factor is e to the 0.12. If I plug that in my calculator, I get 1.1275. Now, if you look at daily and continuously, you'll realize if you go out a few more decimals, they look different. But once you get to daily, it pretty much looks almost, besides a rounding, it's very, very close to continuous. Which means I can tell you I'm charging you 12%, but in effect, I'm really charging you 12.75%. Both of them are true. It's both 12% and it's also 12.75%. 12% compounded continuously will cause your loan to go up by a true amount of 12.75% of the debt in 1 year. Very, very different ways of looking at it. We always want to see our factor and our basic R. So if you received something in the mail that said the loan amount was based on a 12% interest rate, you would also, by law, see that they would also show a 12.75% as well. That's called our APR, our annual percentage rate.